Welcome back to our course on low-level programming. Today we are going to take a closer look at another important part of the software infrastructure that enables you to run your application on the hardware, the operating system. So in our previous lecture we took a closer look at how your programs could be translated from an assembler representation or a C source code representation to machine code that you could execute on your machine. So you had a compiler or assembler that read and transformed your source code files and generated machine files, so object files that had relocatable object code. And then when you had a set of these object files, those were bound together using a linker, possibly together with a set of libraries, and this generated an executable. So today we're going to have a closer look at how this executable can actually be executed on a real physical machine. So we've also seen that this compilation and optimization structure has several steps. So we start from a C file. We have a preprocessor which generates a C file with expanded macros that replace text and header files. This is then compiled to generate an assembler code source file, which is then passed to the assembler to generate a relocatable object file. And you do this separately, this is important, for each of the assembler and C source code files in your project. And only after you've obtained the separate object files for each of your source files, those are linked together to generate an executable. So our compiler consists of two parts, so two large parts. One of those is the front end, which does analysis and transformations to generate an intermediate representation. So the front end checks if there are no lexical errors, so this is part of the scanner. It checks for syntactic errors, which is part of the parser. This generates a tree-like structure of your program, and then it checks if, for example, your types are correct, so you don't try to assign a string to an integer variable. This is part of the semantic analysis of your compiler. We've also seen that it makes your life easier if you split your compiler into a front end and a back end, because you can easily have front ends for different source languages like C, C++, Pascal, Java, whatever. If you have a common intermediate representation for all of your front ends, this makes life much easier, because then you can have different back ends that all read and understand this intermediate representation and generate target code for whatever machine you're trying to compile for. So maybe an x86 Intel or AMD machine, or an ARM processor, or even a RISC-V. So your backend reads the intermediate representation. It does machine-independent optimizations on the intermediate representation. We've seen things like loop transformations, loop unrolling, for example, to optimize, for example, for speed, execution speed, because we can get rid of all these branch overheads. Then it uses some patterns to translate the intermediate representation to assembler. An important step here is to do register allocation, because keeping values in registers is one of the important things to enable that your program can run efficiently. And then you can also do machine-specific optimizations, which are related to the architecture your code should be executed on, so you can optimize the generated assembly code also. So we've seen that this assembler is part of your compilation toolchain, and we've also seen that very often our compiler actually omits the assembler step, so it doesn't generate an S file unless you ask it to do it explicitly, but it automatically and directly generates object files. This saves the generation of intermediate files. This saves process calling overhead for executing the assembler. But if you want, you can still run it this way by generating a separate assembler source code file, then manually run the assembler to generate an object code file. This is absolutely identical. We've also seen that our assembler is a very simple piece of software compared to a compiler. So the first pass of our assembler just goes through your assembler source code and figures out all these symbols. So anything that relates to a number or memory address, like the address of a memory area that's called vars for variables, and the addresses of loops that identify the addresses in memory where the following instruction here is located. So it would consider vars, loop, and end as entries in the symbol table. Here we've shown loop and end to resolve jumps, which happen here and there. And then in the second pass, our assembler just makes another pass through the assembler source code, decodes the mnemonic. This is a simple table lookup, so each mnemonic corresponds to a certain opcode your processor can execute, so to a certain binary pattern your processor understands. It encodes register numbers. For example, R0 might be encoded as 5 bits having the value 0 in some position, and it consults your symbol table to figure out how these textual label names, for example, and of course label names referring to data objects like variables here, can be replaced. So it knows after the first scan that end is address at address start plus 28, and that loop is at address start plus 12. So in the second step, all this can be just replaced, and then each of these instructions, usually on an ARM, results in a single machine instruction, which on Thumb-2 architecture like the ARM Cortex-M usually has 2 bytes, but some instructions take a bit more space, so there are some 4-byte instructions in ARM Thumb assembler. Other processors like RISC-V, for example, commonly use 32-bit instructions. Also the bigger ARM processors in 32 and 64-bit non-thumb mode also use 32-bit instructions. So it really depends on your specific processor type what the output of your assembler is, but in general it's always a relocatable object file, and this has to be linked. So we've seen that when we go through it in the first step, we substitute our labels here with addresses. So start plus 28 is end, start plus 12 is loop, and then we go through it. So when we want to access data or code defined in a different assembler source file, well, our assembler, like a C compiler, only operates on a single source file. So essentially, we need to indicate in our relocatable object file that there's actually something like an open unresolved reference, so the linker can actually resolve this later. So, for example, you have a function here, so some assembler code, which starts at the address we indicated using label 2, and we want to use this code, which is located in file 2, from file 1, so we jump to it using this branch instruction here. So when our assembler tries to assemble this code here on the left-hand side in file 1, it figures out, okay, label 2 is never defined as a label in my source code file, so the assembler simply assumes it has to be defined somewhere else. It's an external reference, so it marks label 2 as being external, and then when we link these two files, or the object files generated from these two files together, our linker can then look for label 2 in all the other object files. It finds it here and replace label 2 by the address of that instruction here. This is, in a very simple way, how linking actually works. Of course, there are more complex examples, but we won't go into detail here. If you're interested, some of these details are discussed in my compilers lecture. So the linker needs to resolve all the references, so we pass all of the object files our projects consist of and all of the libraries we require to be part of our project to our linker, and then our linker takes these, sorts them in memory, and generates one single executable file. So we've seen that all the object files consist of several segments, so text segments that contain the opcodes of your machine instructions, data segments contain stuff like strings or space for integer variables, stuff like that. So all the text files are combined in one big text segment, all the data segments are combined in one big data segment, so it's reordered. Then it figures out the start address for all the modules, and then it combines the symbol tables. It tries to resolve all the symbols, And if this has been successful, so if there are no unresolved symbols, the linker can transform relative addresses to absolute addresses, so it knows where exactly in memory your data encode is located. And if it can't find a label or a symbol in the joint symbol table of all your object files, then either you did a typo or you forgot to include a file or a library, so it produces an error message and doesn't generate an executable. Because if it would generate an executable with an open reference and this reference would then be dereferenced, well, your program might crash because your computer doesn't know where to jump to. So essentially, what we want to do is to see how this integrates with the rest of the system software and how the code generated by your compiler actually interacts with the operating system that's responsible for running your code.